There we go again. Okay. So, full screen this. Where's present? All right. Welcome. My name is Mark. I'm going to talk about some breadboard analog circuits, and we'll do some Eagle for the next 2 hours. This is logic, noise, CMOS, musical circuits. So some background about me. I'm graduated from ITP in 2013, and before that I went to school for electrical engineering, where I delved deep into kind of how analog synthesizers and modular synthesizers are built. So I'm kind of going way back to what I did before ITP, and I feel like a lot of this stuff is not really like covered anymore here because there's no programming involved. It's all like sort of just voltage. A lot of the chips that I'm going to show you are logic gates. So kind of the basic fundamental building blocks of computers, AND gates, OR gates, inverters, and you can use them to create really interesting sounds. Cool. So I'm going to go through this assuming that you guys have some knowledge of like basic electronics and basic music, but if I glaze over something, like feel free to stop me at any time. So, all right, awesome. So the first thing I want to talk about is sort of the concept of analog versus digital. And when I talk about an analog signal, I'm talking about strictly like a voltage. So we're taking a voltage and we're manipulating it. Whereas for a digital signal, you're taking ones and zeros to recreate some sort of audio signal, right? So even though we're using logic, kind of on-off logic, we're dealing with very basic voltage. So we're going to be manipulating that. We're not going to be doing any sort of like digital manipulation. This is a synth block diagram of what a modular synth might look like, and there's many examples of this. So if you look at something like a Moog and you have all of these different plugs that can plug different modules together, it's sort of because each thing is encompassed in its own block. So we have the keyboard here. The keyboard sends a voltage to a VCO, and this stands for a voltage-controlled oscillator, right? So like a sine wave, a square wave, some kind of an oscillator. These oscillators can be tuned to each other, they can be detuned, they can be harmonized, and then they go into a VCF, which is a voltage-controlled filter, and this sort of changes the timbre of the waveform. So this is how you can get the difference between something that sounds like a trumpet versus something that sounds like a violin, right? You're kind of filtering different frequencies out of the tone. And then a VCA, which is a voltage-controlled amplifier. So that means when you press on the key, you hear the signal. When you don't press on the key, you don't hear the signal, right? The voltage is what's amplifying it. So those are kind of the three fundamental building blocks I'll be talking about. ADSR stands for attack, decay, sustain, release. I'm not going to be building those building blocks, but I'm going to show you some resources at the end of this that if you want to go deep into kind of synth land, there's a lot of rabbit holes to go down. Okay, first things first. This is not a CMOS chip, but I find this circuit to be extremely useful. And I'll show you on my circuit board. So there's a little bit of a lag here. Let's see if I can get this. Oh, you know what? This is actually a movie file. That's why. Let's open up a new movie recording. There we go. All right, so over here on the right-hand side of my breadboard is my amplifier. This is an LM386. They're really common, and they're audio amplifiers. This is my speaker. This is just a breadboard-mounted speaker, and I have a little trim pot here to control the volume of the input. So all of the circuits I'm going to be building, I'm going to be running through this amplifier. And I actually like to use this amplifier a lot, so if you're prototyping these things, you can just have it on your breadboard. You don't have to have an external amp. to hear the sounds that are going on. If you look at the circuit, on the left-hand side is what you would find if you looked this chip up in a data sheet, right? This is actually what it looks like looking down on it, and you know which end is the top because it has the little kind of cutout at the top. It might be a little bit hard to see on the camera, but if you look close at every chip, it has sort of either a notch or a dot denoting what pin number 1 is. So if I were to look, I have pin 1 and 8 are my gain. Pin 2 is an inverting input, and pin 3 is my standard positive input. 4 is a grounded pin. 6 is my VS, which is my supply voltage. This chip can operate anywhere between 5 and 12 volts. Probably even go up to more. It's pretty resilient. I typically run it off of 9, but 5 is fine. And then the output comes out of pin 5. I actually am not using pin 7 here. But looking at the circuit diagram, they just have the amplifier, right? That's this triangular portion in the middle. So you can see your non-inverting input at the top, the regular input at the bottom, and this is our output pin. So conveniently, they'll label all of the pins going around. So you can see, okay, 1 and 8 are my gain pins. So there's a capacitor here that changes the gain of the amplifier, right? And I can change this capacitor out to make this louder or softer. Here's my input that goes into my potentiometer, right? Here's a 10K potentiometer, and that's trimming my input signal. Pin 2 is grounded, pin 4 is grounded. Pin 7 is an optional bypass capacitor. I've never found this to change the sound that much, so I don't include it. And then on the output pin, I have a pretty small capacitor and a resistor, and then a pretty beefy capacitor going to my speaker. And this is really all you need to make this work. So I'm going to go over to my circuit here, and this is exactly what I have. This is my 10 microfarad capacitor. That's my gain. Here's my trim pot. Here's my small capacitor, my resistor going to ground, and here's my large resistor going to my speaker. So this is the entire circuit right here. I guess I can play this for you so you can see how loud it is. So it's a pretty steep volume cutoff, and this is because I'm using a linear tapered potentiometer, right? Now, in audio, because your ears hear volume logarithmically, with a linear tapered pot, you're not going to get a good roll off of volume. I should really be using a logarithmic tapered pot here, and you would know that by if you were picking up a potentiometer and you said, okay, I need a 10K potentiometer. If it's labeled with a B, it's a linear. If it's labeled with an A, it is going to be logarithmic. And I just always think like A for audio is the way to remember that. Okay, so that's that. So now let's kind of get into the CMOS stuff. This is the really exciting stuff. So what you heard was this chip. This is the 4106. This is probably the most versatile CMOS chip for audio. There's a lot that you can do with it. It's a hex inverter with hysteresis. And so what that means is hex just means there's 6. So there's 6 inverters on this chip between every 2 pins. You power this pin through pin 14 and you ground it through pin 7. That's pretty universal for almost every CMOS chip. The bottom left pin is ground, the top right pin is pin 14. And really quickly, just to show you on the breadboard, I'm using a 9-volt battery as my supply voltage, and then over here I have a 5-volt regulator that's routing 5 volts in ground to the rest of my breadboard. So I can patch in, you can see power and ground go to every rail, so I can just patch in power and ground, 5 volts and 0 volts to every chip. I like this setup because I can also get 9 volts out of the top if I ever need 9 volts. Cool. Okay, so Hex inverter with hysteresis basically means an inverter is going to put out the inverse signal of what goes into it, right? So if I were to just have a straight wire running from pin 1 to pin 2, I'd get an oscillator on like a megahertz level. I wouldn't be able to hear it, right? So the way to hear this is I set up a resistor and a capacitor to slow down the oscillation, right? And in basic electronics, this is called an RC circuit, right? Resistor capacitor. The bigger the capacitor, the slower the oscillation, right? Because it can take a longer time to charge. So let's see, I have I think a 0.1 microfarad capacitor in here right now. So here's this is my 4106 over here. I know this is going to be kind of difficult to see what's going on. This is my potentiometer, so this is my R, and this is my C. So if I pop this on, this is the frequency I get, right? And I can turn this to adjust it. So it's got a pretty good range. But if I take this capacitor out, and I popped in, let's say, this is a 1 UF capacitor. So this is actually an order of magnitude of 100 bigger. That's my top end of that frequency. And of course I can change my resistor to change the cycle. But I like to kind of play around with different capacitors and see what kinds of different sounds I can get. The general rule is smaller capacitors are for higher frequencies and larger capacitors are for lower frequencies. All right. I'm going to pop that out for right now. So, on the right, this is a snapshot of the input and the output of my inverter. So, on the input of the inverter, as soon as I give it voltage, I'm going to get this sort of triangle wave, right? And this is because this is my capacitor charging and discharging. And what happens is, what hysteresis means is this chip has got a threshold. That means when the voltage hits a certain point, it's going to flip, right? So now, because of that, I can get this really nice square wave on the output. So this yellow is what's coming out of pin 2. A chip, we're going to look later at inverters that don't have hysteresis, and you would get a triangle wave on the output, right, instead of a square wave. You'd get the inverse of the green pulse. So this is the capacitor at its lowest voltage, charges up to the highest voltage, and then as it starts to discharge, we flip down to low. And then as it discharges, this stays low until it flips back to high. And this is happening so fast that it's perceived as audio, right? Cool. Is this all making sense so far? Awesome. The cool thing about the 4106 and why so many people love it is because there's 6 inverters on the chip. So you can daisy chain these together to make really amazing sounds. So here's 2 inverters. I run the output of the first one through a diode into the second. Now, I'm not going to tell you what will happen. I'm just going to play this for you. Jam that in there a little better. So I've got my first inverter here now controls the pitch. My second inverter now controls the timbre. So I've sort of set up a filter using two inverters, right? This is the oscillator, this is the sync oscillator. So you're getting kind of these crazy frequency sounds because you can daisy chain them together like this. The 4106 is really awesome, and you can sort of, even if you Googled 4106 audio circuits, you would find pages and pages of circuits of people who have combined these together in different ways. I'm not going to go too deep into it because there's a lot of other chips I want to talk about, but it's probably one of the more popular CMOS chips for this kind of application. Yes?
So it was controlling the timbre. How is that happening? Is that like a phase?
Yeah, because you've got now two waves interfering with each other. The one wave is going to control sort of like the timbre of the other because you're modulating them together. Awesome. Cool. This is the second chip that I really like. This is the 4040. And all of these chips are actually on, let's see if I have it here, the 4000 series of CMOS chips. They have their own Wikipedia page. They always start with a 4. So 4106, 4040. I talk about these. They're all going to start with a 4, and they're typically 4 or 5 digits long. And you can go through this, and there's hundreds and hundreds of common chips. Not all of them are great for audio, but sometimes you can combine them in crazy ways.
How are these different than the 74 series?
The 74 I know has an inverter that's very similar to the 4106. You can do similar things. There's a lot of different inverter chips that kind of can be built like this. But I don't know if the 74 series has like a decade counter or binary counter. Maybe they do. I don't know.
I've only used the 74 for
Is it the Schmidt trigger?
The Schmidt trigger,
Yeah. Yeah, that is pretty similar to the 4106. Yeah, and they're not the only chips that can be used for this, but this is kind of like the most popular series. So the 4040 is a binary counter, and when you think about counting in binary, right, you have the zeros and ones are duplicates of the bit that comes after it, right? So 001 is half of 010, which is half of 100. So because of this, all of these Q pins are a bit in binary, which means that if I put a clock signal into pin 10, this will go up by a double or a half of that frequency, right? So I'm going to take the output of my 4106 here, and I'm going to put it into pin 10. I'm going to switch over. And so this chip, the second one down, is my 4040. So let me take out my sync oscillator, and I'm going to pop the power back in. Does not want to stay in. Okay. So here's the output of my 4106, and here's the input of my 4040. So now I'm going to take my amp, and I'm going to listen to different pins on this chip. So let's turn this down a little bit. This is my bass frequency. So some of these are even too low or too high to be audible. So because of this now, I can get kind of different octaves, right, of my bass frequency. And the really cool thing is I've pulled out 3 of these pins with resistors here, and the resistors are just to kind of drop the audio a little bit. I can combine these 3 together now to make an octave harmonically, right? So let's see how that sounds. So I can do any combination of these pins, right, to sort of get this now octave harmonic, which is really cool. Pull those out. The other thing I can get out of this is sort of like a clock pulse. I don't know if you guys can hear that. Super low frequency. So because of this now, I can do an LFO, which stands for low frequency oscillator, right? And this is what you hear a lot of the time in synthesizers that sort of have like the drum machine effect, is they're being modulated with a low frequency oscillator, which is a wave that's just not audible, but just enough to send a voltage. All right. So now we can use the 4051. This is a little more complicated. This is an analog switch. And this is sort of like a sequencer, although I have a sequencer chip that I prefer to this, but this can make some really interesting sounds. So on this chip we've got a common pin, pin number 3. And we've got 3 bits here on 9, 10, and 11 that we can put inputs to. Depending on what our input is, it will connect the common to any of these X pins. So for example, C is our most significant bit, A is our least significant bit. If we don't send any of them anything, 3 will be connected to X0. If we put a voltage on B, now we have a binary 2, it will connect this to X2. If we put a signal on C and A, now we have a binary 5, 3 gets connected to X5, right? So it's switching pin 3 depending on the logic on A, B, and C. So this circuit is pretty fun. It's kind of daunting. But if we look at this, right, this is our 4106, this first part. This is our oscillator. And this is our 4040. What I did was I took 3 of the lowest frequencies, 3 of kind of the low frequency oscillators, and I put those into A, B, and C. Okay? So now we're going to be switching at sort of like this rapid tempo. And then all of these X pins just have a resistor on them to change the volume, and it feeds back into another 4106. This is a little bit to take in, but let me play it for you, and you can see how it sounds. All right, so here's my 4040. Here's my 4051, okay? I'm going to take the input and plug it into one part. I'm going to take my output and plug it into the output of this. And now,
can you explain the audio flow of this circuit coming from the oscillator?
so yeah, here's what's happening, right? The 3 inputs that I put to A, B, and C, these are really slow clock speeds, right?
Yeah, the LFO.
Mm-hmm. But they're all duplicates of each other, right? So one might be going like, and the other one's going like. So that means as the 3 clocks are moving, it's creating, binary really quickly, like 1 0 0, 1 1 1. And so based on that, 3 is getting very quickly connected to different outputs, right? Based on those clock speeds. We're going between all of these pins. And I actually only have 3 of them hooked up. I didn't hook up all 8. But let's listen to this again. And based on, let's see where my output is. These are so high, right? It's because these trim pots that I used are only 10K pots rather than 100K. So they don't quite have the range. And then everywhere that I hear that low frequency, it's because I don't have a trim pot hooked up to that pin. So it defaults back to my base frequency. And now my original oscillator becomes my clock. And my second oscillator is the pitch. Cool. I'm just going to put that over there. Cool. Any questions on those so far? So these three chips actually are a taste of when I talked to TK about doing this class, I had been working on, I did a little bit of stuff with the 4106, but I found on Hackaday a blog by Elliot Williams where he goes down this rabbit hole of logic chips. And this is actually a really amazing article. And so a lot of the stuff that I just covered are on these blogs. And he starts with the 4106. So it's kind of serendipitous that he's been doing this for the last 2 months as we've been talking about developing this workshop. So everything that I just did so far is part of this blog series, and it goes even further. It goes into chips that I've never messed with. He does sort of like percussive things and combining timbres. So I would definitely check this blog out. The next couple of things that I'm going to do aren't going to be on here, but this is just stuff that I've kind of done on my own. So I'm going to go back and let's do this at full screen. So this is another chip that I've used very frequently. This chip is called a phase lock loop, the 4046. And what that means is this was used a lot in radio frequencies. What a phase lock loop does is it takes an analog signal and it produces a voltage-controlled oscillator, right? An oscillator that is then fed back into the input to lock the phase together. So it's used for like when your radio is receiving a signal and it has to kind of lock it to a station in your car. That's what's going on, right? So the nice thing is that the 4046 has a voltage-controlled oscillator just built into the chip, right? And it's even a little bit easier to wire because I can just send anywhere between 0 and 5 volts into pin 9 and get an output. So I'm going to unplug these guys. We're going to have a little breadboard noise here. And I'm going to plug in the 4046, which is down here at the bottom of my breadboard. So here's my input. This pot goes to 5 volts and ground, and the middle pin goes to the input. So super easy circuit. 2 resistors and a capacitor. And I have a third resistor going to the pot, just so it doesn't reach 0 or 5 all the way. Let me show you this. So this is a really simple circuit. These 2 resistors determine the range of my frequency, right? So right now I'm using a 1K and a 1 meg resistor. So if I change those values, I can change the sweep of frequencies that I'm using. And then I can try different pots. This is a 100K pot to vary the input. But the nice thing about this is it's very straightforward. I'm only going to get 1 tone out of it. It's only 1 wave. But because I have so much control over the voltage going in, I can almost tell exactly what I'm going to get at the end.
Can you use this to make an LFO?
I don't think you can get that low. I haven't tried. I've actually used 555 timers a lot as LFOs because they have a pretty stable clock pulse. And I'm going to talk about that next. So I've done a lot of things with this chip just because you can control the input so much. You won't get as crazy sounds as the 4106, but I'm kind of partial to this one. I'm going to show you a sequencer that I made, and it was a combination of the 4046 and this chip. So this is another counter, but instead of binary counting, this is just a decade counter. So it'll just go, based on a clock pulse, it will go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then go back to 0. I can change the number of steps with this reset pin. So imagine I only want 4 steps in my sequencer. If I only want 0, 1, 2, 3, then I could take output 4 and connect that to reset. So then it will go 0, 1, 2, 3, reset, 0, 1, 2, 3, reset, right? And it'll reset over and over again. So 14 is my clock, and then these are all my outputs. Now, if you look at this circuit over here, this is the 555 timer clock that I was talking about. Are you guys familiar with this chip, the 555 timer? Really, really super basic clock, right? I'm putting this into pin 14, and then this circuit has got a bunch of LEDs on it, right? So you can see, okay, here's my LEDs sequentially lighting up. You can imagine if all of these LEDs were then run through a trim pot and then all summed into my 4046, how you can get sort of an analog sequencer, right? So let me see if I can set this up for you. Plug that in over there. All right. So this was a workshop we did at ITP Camp 2 summers ago. It was a little intense, but this is the 555 timer. This is the 4017, the counter, and this is the VCO. Here we have all of our LEDs denoting what step we're on. These are actually just switches to turn the steps on and off. And then on the front, we have potentiometers for each step. So I'm going to turn this on, and I'm going to run this through another amp that I brought here. So, what's going on here? My 555 is my LFO, my low frequency oscillator. So this pot on the right-hand side controls my clock speed. And this is part of the 555 circuit. The clock goes through the 4017, and then all of the outputs run through all of these branches. And I could adjust these pots. Now, this rotary on the left-hand side is controlling where the reset pin goes. So I can click this and make my sequence super short or super long. All right, I'll turn that
How
on.
does the individual step work? The turning off each individual step, how's that?
So if I flip a few of these off, it just disconnects the voltage from going through that step.
So that's between the 4017 and the LED.
Yeah. And I'm going to show you the circuit for this, and you can kind of get a better idea of how this goes together.
And so if you give 0 volts to the VCO, you'll just output nothing?
It does output a very low voltage, and I could probably like manipulate these resistors to make that inaudible, but because it's 0 volts, you're still going to get a little bit of a sound on the output. So, whoa, this is the Eagle schematic for this, which is cool. You guys are all going to know how to do this by the end of this workshop. This is a little daunting, but this is divided up into sections. So here's our 555 timer. Over here is the counter. Over here is the VCO. And then just to keep this nice and clean, we routed all of the outputs to their own separate circuits down here. So here's the switch, right, that just opens the circuit. And then it goes through an LED to light it up. It goes through a potentiometer. And then another diode into the VCO. And the diode is just to prevent voltage from coming back into the 4017. Cool. All right. Let's see. Before we start Eagle, there's one more chip that I really like. This was the first fuzz pedal I ever made, and this is the 4069. Also an inverter, but because there's no hysteresis, you're not going to get those nice square waves on the output. But what you can do is keep feeding every output into the next input to create kind of gain stages. And let me see if I can replicate that. You don't hear it so much on square waves as you would on a guitar, but perhaps we can.
So what is the stereosis for?
This is another inverter, right? It's very similar to the first inverter that we talked about, the 4106. But because there's no hysteresis, you're not going to get, here I'll show you, this nice yellow square wave output tone, right? You'll get a triangle pulse that's the exact inverse of this, which can be nice in some applications if you want a triangle wave. But what I really like it for is daisy chaining all the inverters together to create gain stages. And I'll show you how that sounds. So, let's see, I've got one more cable here. So this is a little box I made that allows me to kind of connect inputs and outputs with guitar cables, and then it has breakout wires. So if anyone's into making kind of guitar effects, this is a really handy way to test out your circuit before building a box out of it. All right, so let's go, we'll go the input into here, and I'll take the output down here. Okay, this is my 4069 up here, and I'm using 4 gain stages now, and this potentiometer is adjusting my gain stage. So first I'm going to just play the sequencer normally. And now let's see how this sounds. Yeah, not much change here. So you can hear this adjusting the gain, right? But we're not getting any of the nice fuzz effects that a guitar would produce. Anticlimactic. If anybody has a guitar, we could test that out too. But this is a really cool chip if you are into making distortion, fuzz, overdrive, things like that. All right. I think that's everything, right? Yeah, so this is that circuit. So we keep connecting the outputs of the inverters to another inverter, right? And you can use capacitors to sort of create filters. So the 4069 can sort of shape your sound as well. But generally, you'll see these being used for overdrive, sort of like really harsh guitar circuits. Yes?
Are you just kind of resulting in louder, like more amplitude?
Yeah. And
versus making it more like a square wave?
yeah, well, eventually, right, if you had like a sine wave and you amplify it enough times, it becomes a square wave, right? Because you just chop off the top and the bottom. I guess with more harmonics, it's more evident like how this sounds. Maybe I can feed in, let's see, my my double inverter here into this. Let's see if this sounds any better. It's a little bit harsher right there. Kind of drive it at the top edge. Anyway, yeah. Cool. So that's all that I have as far as presentation goes. But there's like a lot. I want to give you guys some resources. In addition to this blog that I would recommend as a good starting point, because this is sort of where I would go as a beginner. There's also Music from Outer Space, which is Ray Wilson's website of synth DIY circuits. And there's hundreds and hundreds of circuits here. And they're not all CMOS circuits. There's a lot of just straight transistor circuits, everything audio related, but you can almost find anything you're looking for here. Ray just put out this book, Make Analog Synthesizers. You can pass that around. There's some useful things in there, especially for building like a modular synth from scratch. I first started with this book back in 2009, and this is called Handmade Electronic Music by Nick Collins. And this is really, really introductory. Probably half of the book is almost stuff you guys already know. But he does have a few interesting schematics in here. So I thought it was a useful read. It also comes with a DVD of like how-tos. All right, cool. Let's build something in Eagle. You guys have any questions about all this stuff so far?
I was curious about the schematics that you were showing that I think you said were in Eagle. I noticed that the location of the pins, the orientation of them on the diagram is different.
Like this one in particular?
I think it was on the third one. Yeah, that one. The one, the clock pin is oriented in the top left, and then when it's on the board, it's on the bottom right. Isn't that true? Is that right?
Yes. So typically, Eagle parts don't look like the chip. And it's because, like, see, this is in order, Q0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's not how they are on the pins, right? That's actually 9, 7, 6. You can see them labeled here. That's the actual pin number. They do this so when you're connecting them together, it's very clearly labeled like, okay, this is what this pin is. So almost, even the 555 timer, you'll see like, it doesn't look like how the chip layout actually is. That's why I kind of go back and forth between like the data sheet and the diagram, because you want to know like where that pin is when you're prototyping versus an Eagle.
I guess I was curious about if that's a convention of Eagle or whatever,
So Eagle actually has two distinct parts, right? There's the schematic and there's the board. So when you're placing parts, there's actually two diagrams associated with it. There's the diagram that you would see in something like this when you're drawing your circuit. And then when you convert it to a board view, that's when you'll have the actual pin layouts for placing the parts down. And I'll show you those too, and they actually just tie together really nicely. All right. Has anyone here used Eagle?
For years.
Good, okay. Has anyone here used fritzing? Do you guys know what fritzing is? So fritzing is like an open source prototyping software that I actually would encourage, because instead of having two views, you have three. You could start with the breadboard, and it will then go to schematic to board, which is really nice. If you're getting boards produced somewhere, almost every single fabrication house will take Eagle files. I'm not sure about fritzing. And almost every manufacturer has Eagle libraries. Some, like SparkFun, I think, and Adafruit now have fritzing libraries as well. But Eagle's sort of the industry standard. But fritzing's nice. You can make pretty breadboard diagrams with it. All right. Let's do something new here. I'll save these. Okay. What kind of circuit do you guys want to make? We're going to make a 4106 circuit. Let's do something like, let's do that one. Well, I guess let's start with this and we'll see how far we get.
Does anybody need to install anything? So you take 5
Yep. We'll go to the website and
That was really cool.
oh, cool, man.
Thanks a lot, man.
Yeah. Yeah, email me if you have any questions.
I have a million questions.
Awesome.
I just want to start a shit like that for sure.
Yeah.
Cool.
It's-
Thanks a lot.
Yeah. This is kind of obvious, but you guys want the freeware. Don't pay for the $400 version. You know, unless you're gonna like use it a lot and make gigantic boards. While you guys are waiting, I actually brought another circuit that I forgot to show you. This is another 4046, the phase lock loop circuit. But I wanted a way to trigger the oscillator using a piezo. So here's a piezo transducer. So this took a couple iterations to figure out how to get it right. And what I ended up doing is running the piezo through an op amp, which is this chip on the left, amplifying the signal, and then running both of them through a transistor. So let's see what this one sounds like. So I can change the pitch of my oscillator, and that's the same as the 4046 that I used before. And then these two knobs control sensitivity and decay. So I can make a long decay or a short decay based on how hard I hit the piezo. And so I found this circuit because I was looking for voltage-controlled amplifier circuits, and I just Googled simple VCA, and this is what I got. And so there's a transistor here. I sent my VCO into this pin, and here's my envelope. This is my piezo that's amplified through the op amp. And my output, I get this nice decaying oscillator. And so this is a nice, quick and easy voltage-controlled amplifier, just one transistor, one diode. Pretty straightforward.
What about voltage control filters?
So let's see. I think the 4106 has a nice VCF. And typically, you know, you can Google any of these chips. I built a VCF a couple of years ago using 4106, but I don't remember exactly what the circuit was. I think the 4069, the fuzz chip, will do this too. Let's see. I know you can make nice low-pass filters or high-pass filters with these. But yeah, I don't really have a good VCF circuit for you guys today. This is a 4106 as well. All right, how are we doing with Eagle? Ready to roll?
Just updated to 17. Saying that
Permission.
I have to change permissions in the folder. If your application is in the folder, probably set to read only.
That. So I'm going to start a new project here, which essentially just creates a new folder. You can see I have some files here that aren't in project folders. You don't really have to have a project folder. You can just create the schematic and the board, and as long as they're in the same place, they'll be tied together. Let's call this one TP demo. So, you guys all with me? All right. If I go to new, project just creates a folder. Schematic is probably what I want to start with. Because whatever I create in the schematic can generate a board file automatically, I don't need to generate a board file. In fact, it's probably more of a pain because you have to go back and kind of tie them together. So always start with a schematic. And this brings us back to this screen. So, if you guys have ever used like Photoshop or Illustrator or anything that looks like this, you're going to be really pissed off because you're going to find that like the controls are not what you want them to be. Eagle is really, really difficult because you can't just like do the things that you could do in Photoshop. I'll show you what I mean by this. So there's kind of a lot going on the side. What I'm going to do first is I'm going to add a part. And the first thing is I'm going to go to add, which is this little like kind of plug with a down arrow. And it'll bring up a dialog window. These are all of the parts that I have installed on my computer, which includes a lot of libraries. All these SparkFun libraries. There's an Adafruit library. I think there's only one. But anywhere that sells electronics typically will have an Eagle library. And if they're up to date, which SparkFun and Adafruit are, it'll be current with the products they're selling, which is really nice because you can buy a part like some random motor shield, and if you want to build a board with it, you can just go into the SparkFun and grab that board. So let's see what I have in here. Let's see, SparkFun boards. Oh, here's an Arduino Mega. There it is. This probably has the footprint for the entire Arduino, right? If I wanted to include that in like a shield or something. So here you go. Here's your quick prototyping Arduino shield. This is what you would see in the schematic. This is what you would see on the board. You guys probably don't have these because you would have to install them manually. But if you did want to do that, you could just Google SparkFun, Eagle library, and you'll find it on GitHub, and there's also a how to install and set up the SparkFun libraries in a tutorial. Drag and drop them into the Eagle folder. So you guys can follow these instructions. Anyway, let's find a 4106. So down here in my search bar, Eagle is going to look for exact matches for whatever you type in here. In order to search for anything that includes this, use an asterisk. So if I type 4106, let's see if I get anything. If I don't use an asterisk, I get nothing. Nope, where'd it go? If I do use an asterisk, I have 2 results. You guys have these? Cool. These are probably the same. I'm going to drop down the arrow here, and I'm going to look at these 2 options. So I've got an SO14 and a DIL14. So can you guys guess what the difference is between these? Just looking at the 2 parts.
What surface mount and through hole?
Exactly. So this is a surface mount. This is a through hole. Super easy. Probably not for this chip, but I've known a few chips that are out there that have totally different pinouts for the surface mount than they do for the through hole. So if you're ever doing transitional stuff, just be aware of that. You might want to like change the Eagle part. So I'm going to double click on the through hole. And I just get 1 inverter. So I'm going to drag this around until I click. And when I click, now I get another inverter. So what Eagle allows you to do is place all 6 inverters, right? 1, 2, 3, 4, 5, 6. Now if I click again, I'm going to start a second set of 6 inverters, right? So to stop adding parts, I need to not be on the add button anymore. So I'm going to click on the I for info. So I'll go through these one by one. If I click on I, and then I click on one of these, I can kind of get part information, properties, the position, the angle, the name, it's IC1. For resistors that I'll show you a little later, it'll also have value, which is nice because then I can put in the value of my resistors and capacitors. Okay, so let's cancel that. Now let's say I want to move these, right? It would be nice if I could just like drag them around, but unfortunately I have to go over to this little move icon first and then move this, right? So whatever I have highlighted on the left is the action I'm going to perform. There are ways to hotkey this stuff using, I think, a sign, where you can say, okay, I don't have time for this, I'm going to make my own commands. So I added, Command G for group, Command I for info, Command L is a wire, Command M to move, Command R to rotate. And I just kind of set those up myself. Okay. I'm only going to deal with this one, so I'm going to move the rest of these kind of up and out of the way. Okay. So, I need to build my circuit, right? So for this particular circuit, let's take a look. We've got a capacitor and a potentiometer, right, for this guy. So let's start with the capacitor, because I think that'll be a little bit easy. So I'm going to go to add part again. I'm just going to put cap with an asterisk. There's going to be a lot of capacitors. I'm going to close all these. I'm actually partial to spark funds, resistors, and capacitors just because they're really easy and I can see what they are. I'll just show you for reference, but we could use something that you guys have. So here's SparkFun's list of capacitors. And the only difference is the board size, right? So here's a bunch of surface mount capacitors, different sizes. Then I get a bunch of through-hole capacitors of different sizes. And then down here I have another category for polarized capacitors. Surface mount and through-hole. So when you guys install this, which I really recommend, I would use these. But I'm sure we could find something here that we all have right now. Did you guys find one that you like? Here's capacitors with the European symbol. Three pins, that's interesting. You know, it really doesn't matter so much so long as we've got a board layout that we like, right? And honestly, I've got two holes. I know what capacitor I'm going to put in there. So as long as I've got two through holes that are relatively close together, I'm happy with that. So let's grab that. Permission denied. Maybe we can't use that library. All right. Everybody get a capacitor? Cool. So because it's the first capacitor I dropped, it automatically becomes C1. So Eagle is going to count your parts just sequentially as you drop them into the scene. Let's give this a value, right? Over here, this is a 0.1 UF microfarad. So what I'm going to do is I'm going to click Info and then click on my capacitor. And now I've got this value dialog box. The only way you're going to see the value is when you print the board and you select this to be printed, right? So it's for people to see when they're soldering this together, what value capacitor that is on the silk screen of the board. So I can put 0.1 UF. I can put space if I want. It really doesn't matter. You're only going to see that on the silk screen layer. All right. And now let's add a potentiometer. So I'm going to do the same thing. Back into add. I'm just going to search pot, asterisk, and let's see what we got here. Here's potentiometers. So these are nice PCB mount potentiometers. If you have them with just the pins that can go straight in. They even leave room for the layout of the potentiometer, right? So this will show up on your board, which is nice because you know how much room this is going to take up. Maybe you want to mount your potentiometers to an enclosure and just run wires. In that case, you can probably grab something like, let's see. I just saw one. Well, like 3 holes straight across, which I don't see here anymore. There we go, like that. So there's a pot, but that doesn't take up much room on my board. So if I wanted to run these wires to like an enclosure, that would be a good option. I'm just going to pick this one, just so I can see it. Say OK. And I'm going to drop that right up there. All right, cool. So we've got a capacitor and a potentiometer. All right. I want to rotate this potentiometer. So my little rotate tool, and I can spin this whatever direction I want. Move it over here. All right. Now it's time to connect these together. So I'm going to look at my circuit, right? What is this? You guys know the word for this? It starts with an R. The rheostat, right? When you connect the middle pin of a potentiometer to one of the outer pins, so you've only got like a variable resistor, they call it a rheostat. So what I can do here is just connect pin 2 to pin 1. So down here, next to the T, this is the text tool, this is the wire tool. Wire tool, like everything in Eagle, is a little counterintuitive. I'm going to click on the place that I want to start my wire. So I'm going to start on the middle pin here at 2. Now, as soon as I click, this wire will follow my cursor everywhere, right? So if I want to make this wire super long, I can do that. It's also only going to angle at the top of the screen. So see here, I only have a 90-degree angle selected. I can select these different styles of bending. I can have curvy and S-shaped bends if I want as well. Here on the schematic, it doesn't really matter. This is just kind of for your own documentation, but when it comes to the board and drawing traces, changing your angle would be pretty important. When I click again, the wire will stop. So I'm going to go up to pin number 1 and click. But now I've got another wire, right? So in order to make this go away, I just double click on the same spot. And now my wire is done. So a single click lets you keep wiring, whereas a double click will end the wire. Not a super intuitive way to tell you if that's connected, right? It looks connected. I'm going to move the potentiometer and see what happens. Cool. So it is connected. I do this still for every single piece because sometimes you don't actually click in the right spot. Maybe you click one place over and it looks like it's connected, but it's not. The other way to solve this problem is to use junctions, right? So 1, 2, 3, 4, underneath the wire, we've got the junction tool. And this is just a little dot. And I can place this at all the points where the wire meets the part, just to ensure that they're connected.
It's optional, right? It's necessary they have to.
It's not necessary. They'll still be connected. If you run an error check, Eagle will be like, there's no junctures on these parts. But everything can still come out all right if you don't use them. I like using them because sometimes I'll have lines that cross each other. And you know that they're connected when you see the junctions, but they're not connected if you don't see the junctions. All right, now we're going to connect the input of the inverter to pin 1 and the output to pin 3. So I'm going to do the same thing I did before. I'm going to run this up and double click on the junction, and then I'll do the same thing over here. All right. Now, if I just move my capacitor and just place it right on this line, it should be able to just connect right in, right? Let's see. Yeah, it even created the junction for me. Now let's say this is a bit crowded. I kind of want to move my capacitor further out, but I kind of want to keep my lines really nice. I can just use the move tool to kind of move my lines and make this a little bit nicer looking. And everything will stay connected. I can kind of put this wherever I want. Okay, so my capacitor goes to ground, right? So I need a way to tell this where ground is. The nice thing about Eagle is that everything that has a ground or a supply voltage will be connected together. So I can go into add, and I can just search for ground. Or just GND will probably give you better results. And there's going to be a bunch of different ground symbols. You can get them with or without pads. Now ground, I don't have a board image, right? Because when it comes to the board, Eagle's just going to draw all the grounds together on the same trace, right? So I don't need to worry about this. If I did want ground with a trace, you could see here's one that has a hole for ground in case I wanted to like patch things into ground. But typically, we could just grab any of these supply symbols. And I can throw it on the bottom of this capacitor. And that should do it. how do you delete? So X, press the X and then press what you want to delete.
X.
This X tool right here, next to the add tool. Ah, should update Eagle. So notice I deleted that, and then I added it back in, and it kind of double checked to make sure I want to connect this net on the top to this net on the bottom. So I'll just say OK. And now it'll connect them together. All right. Everybody good so far? Do we have an oscillator? A really nice thing you can do with Eagle to make these schematics look kind of nice is not connect everything together with lines. We can have labels that route things to each other, right? Because schematics can get really crazy, especially with all the wiring going on. So rather than connect this directly to my next chip, I'm going to draw just a short segment here, and I'm going to name this segment. And then when I draw my next circuit, I'm going to name that segment. Because they have the same name, they'll get connected together on the board. So, over here, there's two little resistor symbols. One says define the value. The other says define the name. You guys see these? Click on the name. And then click on this little short segment we just wrote. So I'm going to call this VCO out with an underscore. Now, I don't know what the name of this is. If I went to info and clicked on this, its name is VCO out. But in the schematic, if I want to know where the signal is going, it would be nice to see its name written here. So there is a tool down here, right next to the junction. It has a little ABC. This is your label tool. So I'm going to click the label, and then click this segment, and there's my name that just pops up. So now I know that's VCO out. If I see that again, I know that those two are connected together. Questions so far? Under these two little stick figures is rotate. I think most of the people getting started with Eagle, their biggest problem is like the interface. So it's really like,
I use exclusively the command wire.
yeah.
You can also right click. Updating.
All right. There's another problem with our circuit so far. Discounting the counterpart that we haven't gotten to yet. What's missing from the 4106?
Power.
No power and ground, right? Almost every chip, Eagle won't display power and ground unless you want to see it. I like to see this in my diagram. Also, I'd like to know where they're connected to on the board. So there is a command called invoke. It's these four little icons kind of clustered together. If I click invoke and then click on this, See how it'll give me these, but it'll say power by request. That means I'm going to get my 6 inverters, but it's not going to give me power unless I ask for it. So I say OK, and now I get these 2 little lines that give me power and ground. You guys remember which one is which? 7 is ground, right? So I have ground down here. Rather than go into my parts library, I can click these 2 little stick figures, which is copy. I can copy that and just drop it right there on 7. Ground is easy because ground is always ground. No matter what part in the Eagle library is going to be ground. But for supply voltage, I kind of like to do this manually because I want to know what my supply voltage is. You can get a VSS icon in Eagle, but I'm just going to do it manually. So I'm going to draw a little line here, and I'm going to name this "5 volts." And I'll label it so I know.
How do you do the 6?
So I did the same thing I did over here, right? I drew a little line, and then I clicked on name, and then I named this segment just 5V, and then I used the label tool to show that 5 volts here on the diagram.
Where do you get the power from?
Okay, so here, this command with these 4 little icons here is called invoke. If I click on invoke and I click on any of these inverters, I just use the main one that we're using here, you'll get this little dialog box, right? This shows you that these gates you're going to get next after you click. So you'll get 1, 2, 3, 4, 5, 6. But this power you will not get until you request it. So if you hit OK or show, then you'll get these 2 vertical lines that denote power and ground. And actually, the first version of the sequencer that we made, we didn't invoke any of the chips, so none of them got power or ground, and we couldn't figure out what happened. Okay, before we do anything, before we finish the schematic, I'm going to generate our board file, and I want to show you guys what it looks like. And now, after we generate it, we can swap back and forth and sort of rearrange things on the board. So all the way up here at the top, next to this sheet number, there's like a little chip icon. It says generate / switch to board. Click on that. And it'll say, this board does not exist. Create from schematic. And I'll say yes. And now I should get this window. You guys all have this? Cool. Yeah, so up here, see this little icon with the little, kind of the chip and the icon above it? I guess it looks kind of like an AND gate. That will generate your board file. And now I can use this to go back and forth between them, now that I've generated it. Okay, I can use all of the same commands. So I can use my move tool. This is my board area. If I try and put this not in this box, it's going to give me an error. I can't, you're not outside, you're not in the right area. So I have to place all of these in here. However, because my potentiometer's pads are all the way at the bottom of this, let's say I want to place this at the top of the board and have it hang off. I can put it there. The silk screen can extend off of the side of the board, but the pads can't, right? When I say silk screen, I'm referring to like this white outline. All right. So these yellow lines are our connections. We haven't yet drawn the traces. If I have a lot of parts going on and my wires are all kind of messy, there's a command called rat's nest, which will essentially untangle them as best it can automatically. It's the third command up from the bottom. It says rat's nest if you hover over it. Probably nothing's going to happen because no, it moved my capacitor ground over to there. But it'll just calculate the shortest possible connections to every piece. It's really convenient when your boards get really big and daunting. All right. Let's finish our schematic and then we can lay out the board. So I'm going to go back and I'm going to find my 4040 decade counter, or the binary counter. So 4040 asterisk. And let's see what I've got here. Same two parts. I've got a surface mount and I've got a through hole. Same with this. Going to grab the through hole. Throw it down. Now notice, I didn't have to place multiple pieces. This is just one chip. But what do I have to do still? I'm still missing power and ground, right? So I have to invoke this one as well. So there it is. If I invoke this chip, notice I get the chip by default, but power is still by request. Say OK. And I could just tie this into my other power and ground over here. Just use wire. If you're not sure if these got connected together, you can go to your name and say, okay, good, this is ground. Cool, it's connected. If I click on the name of this, this is 5 volts. Awesome. So it automatically named these correctly, which is good. Okay. So I don't remember what my 4040 is. Which pin is which? I'm going to go to my schematic. I'm going to say, okay, cool. Looks like the output of my inverter is going to go into 10, and my 11 pin gets grounded. And then these are all outputs. So I'm going to go back, and in my interest of keeping everything nice and clean, rather than just connecting this line across, I'm just going to draw another short segment on 10, and I'm going to name it. What is the name of this? VCO out. I have to type this exactly the same. Luckily, these will all be uppercase automatically. You can't lowercase type in this, so that's not a problem. But if I don't have the underscore, now I'm going to create a new net. So I have to make sure I spell this the same way that I spelled the output. So if I type OK here, now I get a dialog box. Do you want to connect this to your other VCO out? So that's how I know I did it right.
You want wire there.
You want this.
Okay.
Because I want to connect this to my other net down here, right? So if I say yes, now if I switch to my board view really quickly, let's check it out.
How can you move only the label?
Let's see. So you want to move this label here?
Yes, because when I click it appears on the chip. So I want to do it like this.
You can use the move icon to just move the label. You got to click it on the little plus. That's its origin. So it should be right under the V. If you click it right under the V, you can move it around. Also, if this is a little bit big, the font size, you want to make it a little smaller, you can use info and make this size like 0.05 or something. And now you've got smaller text. You can do everything with labels that you could do with everything else. So if I want to rotate this, I can rotate it. I can copy it. I can move it. In fact, I can copy it and put it over here. All right. I'm also going to copy one of my grounds and just drop it over on number 11. Cool. All right. I'm going to skip the resistors. This doesn't have to be exactly right. But let's say I want to route all of these outputs to some jack on a box somewhere, right? My board is going in a box, and all my outputs are going to plug into this box. So all I really want on my board are a bunch of holes to solder to. So under my add, I can look for a jumper. And there's a nice jumper library of just lines of holes. There's 3. There's 4 in a box shape. There's 3 for header pins. They give you this silk screen to show you where the header pins go. There's 6. 4 in a row, 2 rows of 4. So there's a lot of different jumpers I can use. They just keep getting bigger and bigger. Let's say I'm going to use 4 for this example. I'm just going to grab that one and slap it down right there. I like to use a lot of jumpers because I make a lot of things that go into boxes. And because of this, I like to label my jumpers so that I know what they are. Because otherwise I just see all these rows of holes that I don't know what they go to. So, I don't know why I keep getting this error. I'm going to click info and click on the jumper. And rather than it being JP1, I'm just going to name it, let's just call it output. And I'll spin it so it's in the same direction as my chip and connect it to the first 4 bits here with some wire. Cool. I should probably mention that technically, I didn't go over this, all of the 4106 inputs that you're not using should be grounded. I'm not going to do this for this example, but 11, 13, 5, 3, and 9, just the inputs. If you ground them, then you don't get that triangle wave that may or may not interfere with the rest of the circuit. Although sometimes it can be cool noise, I don't know. Depends on what you're into. All right, I think we got a circuit. Okay, so let's go back to the board view, and now let's make this look kind of nice. So we've got a nice schematic. Now I want to make my board. I'm going to get it produced somewhere. I'm going to like etch it over there or whatever. So the first thing I'm going to do is I'm going to put everything inside this box. Zoom in a little bit. And now this is sort of like a game of... You can group. We don't have a lot of parts, but this dotted square is the group icon. You just select everything and move it all together if you want. But since we don't have many pieces, I'm just moving them separately. This is like how OCD you want to be, really. With this many parts, you're not going to run into problems, but for bigger circuits, you might have issues. You also need to know before you start this whether you're going to have a 1-layer or 2-layer board, or 3 or 4 layers, depending on how complicated you're going to be. I'm going to put these all kind of, let's see if I can arrange these in something that makes sense. So I'm going to try and make my yellow lines not cross as much as possible. So let's see, maybe like that. And I'll turn this guy a little bit. Put these next to each other. Maybe that guy goes up there, maybe this goes over here. And now, let's see, where should my output go? If I rotate it, maybe I can make this kind of, let's do that. All right, let's put that on the side like that. And I can keep rat's nesting and making things a little nicer. Remember, the yellow lines don't really matter. They're just showing you what parts are connected to each other. What really matters are the traces that I'm going to draw in a moment. Okay, so I'm going to draw traces. Up above the wire tool is the route tool. Okay? You can auto-route this, especially for this board. There is an option to do that. I think it's in Tools. So let me just do that. I'm going to say, oh, come on. No. I'm locked out. There we go. I'm going to say Tools, Auto Router. Let's see what happens. I'm just going to say OK. Oh, it didn't work. Did it work for you guys?
Yeah.
Good. Interesting. I've got some weird permissions going on here. That's OK. I'm going to do it by hand. Auto routing is fine, especially on a small board like this. There's like 5 components. What color traces do you guys have? Do you have red and blue?
Yeah.
Okay. That means you've got 2 layers. You've got a top layer of traces and a bottom layer of traces. Depending on how you're producing the board, that might be fine. If you're sending it away, 2 layers generally is the same price as 1. If you're etching with acid, it's going to be really hard to do a top layer and a bottom layer. Usually it's only 1-layer boards if you're doing it by hand. So I'm going to just do a 1-layer board. I'm going to click on my manual routing tool. Up here, it says 16 bottom. Is that what it says for you guys? This is telling me what layer I'm on, right? I have the option to choose between top or bottom. And if you pay for Eagle, I think you have 6 options. It doesn't matter whether I use top or bottom so long as I stay consistent, right? So I can stay on the bottom or I can just stay on the top. But if I want to just stay on one layer, I don't want to have both red and blue.
Sorry, I don't have that option. You see it here?
You don't have these?
Yeah, how can I
Go to View Layer Settings. So these are the number of layers that you're going to see when you're working on the board, right? So right now, I can see the top traces, the bottom traces, all the pads, all the vias, which I don't have any. Yellow is unrouted, so yellow are the lines that are drawn now. And then all of these gray blocks are the placement, the dimensions, the origins, the names, the values. And then down here, these are all unselected. And so there's a lot of layers that are selected. I'm not going to go over sending this out to the manufacturer, but basically you only want to send them top, bottom, pads, your silkscreen layer, which is generally your names and values, and your drill holes. And SparkFun actually has a great tutorial for that. But if you want to see, like, okay, I don't want to look at any of these white layers right now. I just want to see what my circuit board looks like. I can deselect them, and now I've only got my pads. Okay, I'm going to turn them back on for the moment. Were you able to get your pads back, your layers? You might have to select this first, your manual router. If you have another option selected, you might not have that, right? Okay. Here again, this is my angle of my router. I like this second one, the traditional circuit board angle. But, you know, if you like curvy circuit routes, you can curve them as well. So I'm going to choose the second one. And then I can grab any of these, and now I can start connecting them together, right? So everywhere that I go with this will actually erase the yellow and just draw this new blue line. Let's say I mess this up and I want to get rid of this and route it again. Rather than deleting it with the X, because I still want to keep this connection intact, this tool next to the route tool is called Rip Up. This removes the route but keeps the connection. If I double click, it eliminates the whole route. Right? Let's say I'm doing this by hand, I'm etching it, and I want my traces to be super thick because I'm doing this by hand with acid, and thin traces have a tendency to break if you're doing it manually. What I can do is up here, the width, if I change this to like 0.03, now I get much beefier traces. Although it didn't seem to do much. I think I have to hit enter. Yeah, there we go.
If you overlay a trace, it's like not allowed.
Right. Because this isn't like the schematic view. If this is actually what the board is going to look like. So if you draw a trace over another trace, they're going to connect together. So that's why this part is sort of like a game, because you have to figure out how to connect all these lines without crossing them. So, okay, let's see. Let's see if we can run into a problem like this. Like if I connect power on both chips, now I've got this problem where I have to connect this to the potentiometer, right? Okay, so what do I do? Well, let's see. This is also a problem. One trick is I can go right up to this chip, and then I can change the width of this to maybe 0.15. And then I could zoom in and maybe go between those pads. Right? Now I can make it big again. And I can finish routing this up to here. Right? And if you get these made professionally, all the traces are underneath a layer. So you're not going to accidentally solder to them when you're soldering to the pads. When it comes to sending these away, there are some manufacturers that have clearance issues. So they might say this trace is too close, you have to change this clearance before we can produce this. So that's according to different fabrication houses. Let's see. Let's see if I can finish this. Doop, doop, doop. That was easy. This one's going to have to come up around like that. This can come up through the middle. This is going to be tricky. This can go up there. This will have to go, I think, through here. You probably shouldn't rush through this like I'm doing right now, because you end up with a lot of weird looking traces. All right, and this last one. Okay. Okay. So now I'm just going to show you how to get like a PDF out of this. So in case you wanted to etch it, you have a PDF. So now I have all my traces, but if I want to etch this by hand, I don't want all of the kind of outlines of the parts or the names or anything. I just want what's actually going to be copper. So I can go to layers and I can turn off all of these layers that I don't want. And then I could actually just export this. I can export it as a DXF if I want. These dialogues are really getting annoying. Or I could just print it to PDF. So I can print to file. And when you get to this dialog box, you have to be careful because sometimes there might be an automatic scaling factor in here, which will mess up the size of everything. Or they might mirror it by default, which sometimes you want that, depending on how you make this, right? You want this to be the inverse, because if you iron it onto something, then it transfers it. So just be aware, you know, if you're flipping this, you know, what orientation you want to print it off. It should print everything solid black. So now if I hit OK, I should have ITP demo.pdf. No, where did it go? Let's see. No, it didn't save here. Are you the one? Let's just save this again as something else. Save as ITP demo. Two. Okay. I'm having interesting problems with Eagle today. I can show you what another example looks like. Here's another board. This is just the black. This just shows you what the copper is going to be. And so I could print this off on transfer paper. I can laminate it onto copper. That's kind of a whole other workshop. But now I have my layer, and I can use this. That's sort of like a quick and dirty Eagle tutorial. But it's really like, just takes years and years of fumbling through it before you get good at it.
You don't have shortcuts in Eagle, right?
Shortcuts
Like,
for key commands? I did them myself. If you go into options and you go to assign, you can make your own keyboard shortcuts here. So I made these last couple at the bottom. I made group, move, add, rotate, and delete, like the commands I use the most. And I liked Command M because that's like what I'm used to for every other Apple program ever. So yeah, I use those. I don't have a shortcut for everything, but it helps. Cool. All right.
to bring this circuit, we're missing all the resistors.
Yeah. So I skipped over that part just because I don't know why. It probably wouldn't have been that quick or that slow. But yeah, there's 3 resistors on each of the outputs. Yeah. And really the only reason that those are in there is because if you sum those together, you're going to get the amplitude of the summation, right? So those resistors are dropping down the volume of those levels so that when they sum together, they're not like blown out. But yeah, I mean, you can probably make any of these circuits in Eagle just by going off of a schematic and the parts that just come with Eagle. If you wanted to use things like motion sensors or like electret microphones, you could download the SparkFun or Adafruit library, and they have most of that stuff in there. All right. Cool, guys. Well, I'm going to hang out for a little bit. I'm going to stop this screen recording. And
You're gonna send